Fantastic. Excellent. Okay, thank you for the introduction, Drew. Yeah, so my title has changed slightly. So it's Challenges and Solutions to the Measurement of Low Count Rates in the Field. Excuse me. Thanks to ARPS for the opportunity to present this. I think Drew covered most of my first slide already. I'm currently a senior radiation specialist at Liquid Resources, dealing mostly with mineral sands, and we're currently moving into the rare earth elements. I'm also the co-chair of the WA ARPS chapter, so for all my colleagues in WA, we do this quarterly. We generally meet somewhere with a liquor license and discuss whatever is relevant to the industry at the time. Everything else, I think we've covered. Hygiene, Big Med, yeah. I'll start with an introduction about radiation detectors. So most of this presentation, I'm hoping a lot of it will be revision. What I've noticed, I do a little bit of mentoring over here in WA, is that there aren't many resources to point people at when you say, hey, let's go do a background survey where the signal is really, really close to background, and how do you make a quantitative decision on that? So hopefully this presentation will be a nice refresher for those who already know. And for those coming into the field, how do you deal with the problems of low count rates? Excuse me. So radiation detectors are effectively just counting devices. They just count stuff. What they can count, how they count it, changes from unit to unit, but it's just looking for ionizing events. So a lot of the equipment we generally use came from high flux or large source environments like X-ray tubes and dental, medical, nuke med. You know, these are very, very, very high radiation areas. So your equipment doesn't need to work particularly hard to see it. It's very easy to distinguish the signal from the background. Like if you're getting 300,000 counts and background's 0.7, you don't have to be a rocket scientist to figure out what's going on there. And because of those high count rates, it's very statistically repeatable. So we usually don't report errors in that sort of stuff. Like if you do a gamma survey around a nuke med lab, you'll get 10. You don't get 10 plus or minus 2. From those applications, we generally talk in counts per second, which is, again, a perfectly reasonable unit to use because you've got so many counts in that second. The statistics work out really well. Everything's robust. Great. Everything starts to come undone when the counts are below approximately 10 counts per second and definitely below 1. So we're going to focus on those sorts of situations because much of the equipment that's out there just wasn't really originally designed to do that. So we've got counts, count rate, and dose rate. I have seen that these terms are used interchangeably. They are very, very specific things. So counts would be, I've seen X detection events. It doesn't matter what the time was. I heard it go click 12 times. I heard it go click 100 times. Your count rate, I should also state that your counts can only be positive integers. You don't get 0.5 of an event, and you can't have negative. Count rate, the question would be, I've seen X detection events over Y time interval. Excuse me. Again, must be positive, but this time you can have a decimal. This positive integer, positive decimal will be important later. And then dose rate is usually what we're interested in. Again, if you're looking at high dose rate areas, counts per second, X number of counts per second is Y microsieverts per hour. And that is very specific to that detector and that photon energy. I could do a whole other presentation on that, but I'm not going to. But you would see a calibration coefficient for your detector. It might be 17 counts per second equals 1 microsievert per hour. Excuse me. Those numbers are really good to know, but they do change from unit to unit. So some of the low count rate scenarios that I've certainly seen, pre and post mining gamma surveys. So these are a statutory requirement before and after you do mining. You need to go out, measure the dirt, figure out what areas have got higher or lower based on the geology of the area, excuse me, and then after mining, demonstrate that you've returned it back. So you are trying to find nothing in this case, or you're trying to find numbers very, very close to background. And depending on where you are, particularly if it's a coastal area, you'll see a lot of beach sand. Beach sand's almost got no norm in it, so you are looking at very, very low numbers. And this has been the topic of hot debate as to how do you establish the background for an area based on these wildly fluctuating numbers. Another one is airborne dust filters, where we are looking to count effectively millibecquerels per cubic meter, or millibecquerels in the filter. So that is like one counted event per 1,000 seconds. So it's a very, very slow count rate. Surface contaminated objects, we've got a whole series of slides on this one coming up, because that is, again, hotly debated. At what point do you define something as contaminated? And there are guides on that in the transport regs, but then can you effectively measure at that level? Excuse me. Detection of norm, subsea, or through attenuating mediums. So you've got a client, you might be the client, oil and gas, norm inside your assets, and you want to determine how much is there, and is it safe to work with this material? Is it safe to bring it up? Is it safe for workers to be around it? Norm and hot dirt, sample water analysis, these are usually really, really low count. Again, if you're looking to release something as non-controlled waste, you are looking at very, very low contamination levels, which lead to very, very low count rates. So for all the above that I've shown you, with maybe the exception of the norm stuff, your count rate is going to be less than 1 count per second, and certainly within the range of background. So teasing out your signal from your background will be challenging. So how your meter probably works. Again, this is hopefully going to be revision for a lot of people. Gas detectors, really easy. You've got a volume of gas. Your ionizing radiation comes in. It creates a electron and positive ion pair. There's a high voltage across the top, and that will split your charge carriers, which will be detected as a event, and your machine will go beep. Solid state detectors, and I've got to say these are the semiconductor ones. The scintillator detectors, while solid, aren't classified as this, but it's the same again. You've got a P-N junction semiconductor, voltage over the top, ionizing radiation comes in, creates an electron and a hole in the semiconductor, they're pulled apart, beep. So both of those types of detectors, gas and solid state, they're using that voltage difference and the ionizing event to detect the ionizing event. That is your click. Scintillator detector is a little bit different. You've got a crystal that'll convert from ionizing to visible, usually blue or purple, I think. That'll be converted to an electron. There'll be a photomultiplier tube, which will then escalate that signal to something you can read. But again, it's using that ionizing event to create charged particles. That's a very broad description of how meters work. There's lots of them out there. There's some really good stuff coming out at the moment with the silicon photomultipliers, but I ran out of room on the slide. So what I've got here, I will go into more detail on this Poisson distribution, excuse me. But if you're out in the field measuring a low count rate, and in this case, we're expecting to get 20, so lambda, I'll explain it in a minute, is 20, I'm expecting 20 counts per second. For anyone who's done this, that's actually a relatively high count rate. But you can see here, the red line is your expected value. That's what you should be getting. The black is your what you're actually going to get from second to second. And you can see that it varies by up to 7, plus or minus 7-ish. But the blue one is the interesting one. That's your cumulative average. So I start at time 0. In this case, I've got a couple of really high numbers early. It's pushed my average up to 25, 26, 25. It takes nearly 30 seconds for that to get down to somewhere within 21 and 19. So if you're going out into the field in these low count rate environments and you're just pointing the meter at something, waiting a second, reading the number, moving on to the next spot, your results are going to be all over the shop. You could be reading anything according to this graph from 30 all the way down to, say, 12. And how does that make sense? How does that impact if you'll say this is post-mining rehab? Does that mean you can leave the site and walk away and say it's been rehabilitated, there's no risk? Or have you unfortunately got a 12 when it should have been a 20? I want to talk a little bit about how those fluctuations behave over time. So in the example I gave, 20 counts per second, it will have a standard deviation of about 4.5. We'll talk about that in a bit. So the longer that moving average window is, the more the fluctuations will cancel each other out. And that's all because of the central limit theorem. If you sample from a population long enough, it'll always get closer and closer to that mean value or the expected value. It does mean that we have a burn-in time at the start when the device has not been recording for very long. So you kind of have to work through that. And it could be anything from 10, 30, 40 seconds. It could be minutes. It could be hours. depending on your application. It's why it's so important to know what your count rate is and what your background is, and reverse engineer your tolerances. But the good news is that eventually that central limit theorem will prevail. It'll just take time. The more variable your data is, the longer that's going to take to happen. Again, it's about knowing what you're measuring, how it's fluctuating, and what procedures you can write to sort of iron that stuff out. So I've mentioned the Poisson distribution a couple of times. It is similar to a normal distribution, up at 10 or more. Excuse me. What I've got here is a couple of lambda values. Now, the normal distribution is defined by its mean and its standard deviation. The Poisson distribution is only defined by that lambda value, the expected value. Anything greater than 10, you can kind of call it a normal distribution with a mean at the lambda value, and it will have a set standard deviation of the square root of the mean. And that's what makes this very, very handy when you start having enough counts, more than 10, preferably up in the 40s, is that I know that it's looking like a normal distribution. I know that the mean is the same as the lambda, and I know that the standard deviation is the square root of the mean, which is also the square root of the lambda. The problem is when I've got less than 10, the shape goes a bit wonky. It is not log normal, it is just wonky. And a lot of the assumptions about this being like a normal distribution don't work anymore. So the descriptive statistics for this, your lambda value, your expected value, is the same as the mean, which is the same as the variance, and the variance is the sigma squared. The sigma, which is the standard deviation, is the square root of the lambda. And as I said, as your lambda gets bigger, your probability mass function starts to look like that normal distribution of the form lambda square root of lambda. This isn't particularly helpful in the field, but it does help you write procedures, particularly if you're doing things like the alpha counting that we mentioned before, with one count every 1,000 seconds. So that's the equation of the Poisson distribution. Again, this is not something you'll ever use in the field, but you can see that it's only defined by that one variable lambda. Now, K is your test value. Now, this function applies to things like seconds between calls in a call center, or pieces of chewing gum stuck to a slab on a footpath. Anything that has a discrete number of things, countable objects, you can use this for. Not all cases, but generally. You can't have a negative. Technically, an incredibly high K value is possible. So the way you might use this function is, okay, so given a lambda of 17 counts per second, if I know that's my expected value, what's the probability of seeing 18? Or what's the probability of seeing 4? And when you, if I can go back, when you put those K values in, or 1, 2, 3, 4, you start to get these curves that we saw before. So there's this is one of the things that I've not found a good reference for when mentoring somebody. So let's chuck 18 in, excuse me. 17 to the power of 18 is a horrifically large number. E to the power of minus 17 is a horrifically small number. And 18 factorial is going to be, again, a really, really big number. Through the magic of maths, they do kind of cancel each other out, and you end up with a reasonable number down here. So what's the probability of getting 18 given my expected value of 17? 9%. 16 and 17, a little bit higher, and that makes sense because they are right near their expected values. There's no 16.5. And it goes down as you move away from that expected value. One thing to note, while it will only go as far down as 1, it will, in theory, go all the way out to infinity. My experience has been that computers have a very, very hard time doing this for anything bigger than 170. 170 factorial is a number that a 16-bit computer can't actually register, and it will overflow. So just be mindful if you are doing this in Excel or something else like Python or R, there is like physical limits to what your computer can do. So what do you do when that lambda is less than 10? So we've got some assumptions. If it's bigger than 10, we know that it has a particular shape. Great. Less than 10, it starts to look a little wonky. What can we do? You redefine your problem. So up until now, it's been very much a case of counts per second. I can't do much about the counts, but I can do a lot about the seconds. So I like to say that time fixes everything. If you can't do it in a second, you do it in a minute. If you can't do it in a minute, you do it in an hour. If you can't do that, you get better equipment. So let's say we've got a counting situation of 0.6 counts per second. And anyone who's been in that sort of field, and it looks a lot like a beach, you'll notice that your meter, particularly if it's digital, will bounce all over the place. Excuse me. So knowing that the square root of the count rate is the sigma, if I've got a number less than 1, I actually get an error bigger than the value, which is nonsensical because I'm applying the wrong statistics. Anything less than 10, these assumptions just fall apart. If I go counts per minute, this is the same count rate. I get 36, much bigger than 10. My square root is 6, my error is 17%, and that's actually a fairly reasonable response. If I stand out there for an hour, I'll get 2,160 counts with an uncertainty or a sigma of 46, and that's got an error of 2%. Now, that's an unnecessarily accurate number, but you can see that error, while it is getting bigger, it's a smaller proportion of the actual value that you're testing. So when you do any other sort of if you measure something with a ruler, which is plus or minus 1 mil, at 10 mils, it's plus or minus 1 mil. At 500 millimeters, it's plus or minus 1 mil. At a kilometer, if you've got a kilometer long ruler, it's plus or minus 1 mil. The error doesn't change, but in this scenario, it does, and we can utilize that. Environmental gamma surveys, it's one of the applications I said where we do this a lot. So this is a project up in the Gascoyne, excuse me, they've done a whole bunch of grade drilling here just to find out exactly where their ore body is, exactly how the grade changes over depth and longitude. But when they're finished, they're going to have to return all this back to the way that it looked before. Again, the rocks are relatively low norm ironstone. The dose rates can be very, very low. Excuse me again. So you're looking to get numbers that you can put your hand on your heart and say, we're confident that this number is within 10, 20%, and that it looks like it did before we came and drilled all the holes in it. So this site, we had a procedure, I think it was 30 seconds. So you had to stand at every location for 30 seconds. We were using a red-eye GX, which has a really good mean dose rate or mean count rate function. And you can watch it just go up and down, and then just kind of flatten out at all around background. So that's generally the procedure we use at almost every site I've seen. It's just 30 seconds seems to be a nice number. It's a nice trade-off between standing in the field, like a muppet, and actually getting something done. Like the longer you stand there, the better your results. But there's a lot of these you need to do. There's hundreds, possibly thousands of these you need to get covered, and doubling your sample time can quickly add up. So we've already talked about the cumulative moving average. This is a similar example. Again, the expected value is 20. Your actual counts of the black line going all over the place. Your cumulative average is that blue line. But what I've got on this as well is a 10-second average. So it's not every count that I've seen so far. It's just the last 10 seconds. And I apologize if it's hard to read, but this value continues to jump up and down. This is probably what your meter does. It doesn't look at everything it's ever seen. It's going to have some window. Sometimes you can control that window. The old meters used to have a fast and a slow switch. Fast was a very small window, so the meter would respond quickly to any changes, but it meant that if you were in a low dose rate environment like this, it would bounce all over the shop. Put it onto slow, much bigger window, much more smoothing due to the averaging effect, and you get much more predictable numbers. But here you can see with this 10-second moving average, the green line, it's still bouncing well and truly above 21 and below 19 on a regular basis. It's still pretty good. That's 5-10% accurate. I would accept that if I was still a regulator. The other thing we can do is we can target the error that we want. So rather than just getting what we get, we can say, well, how long do I need to be out here to get an answer to, say, 10%? So if we know, well, now we're going to start using some of the descriptive statistics that we mentioned before. So if I want my standard deviation to be 10%, I'm going to need a count of 100 because the square root of 100 is 10 and 10 is 10% of 100. So we count as long as we need to get those 100 counts. Doesn't matter how long it is because we're aiming at a particular error tolerance. So if it takes 20 seconds to get that 100 counts, your count rate is 5 counts per second, plus or minus 0.5. It's a pretty good number. If it takes 10 minutes, obviously you're not going to stand there. You're going to set it up on a tripod and walk away. If it takes 10 minutes, you've got the same 10% error, but you count it down to within 0.16 counts per second, which you're just not going to be able to do standing there for 30 seconds with an uncertainty of far, far less than background. Obviously, you're going to have to do some clever math to get the background out of that. But by standing out there longer, knowing, aiming for a certain number of counts, in this case 100, you can drive that error, which is handy. Generally, we don't do this in the field. We just take we take what we can get because there's a human factor involved, which is standing there with a tripod or standing there in the heat or standing there covered in flies and asking people to stand there for an hour is probably not going to make you any friends. So now that we know all this, we can go a little further. So this is starting to get closer to the sample analysis that a lot of labs do, where they've got an unbelievably low count rate, but they've also got a background in their lab. And the question will be, how do I know that the result I got wasn't just a background fluctuation? And how do I know that what I got is my signal? And those are two different questions. So the first one you have is a false positive. So it might be a background count that is just abnormally high, and it will happen. And that's a type A error. So your background might be 10, you've got 15 counts, you go, yep, that's great, but it might just be a randomly high background. The other one is a false negative, where your background plus your sample gives you, for unknown reasons, they're both just low at that time, and you get a really low number. So you might get, say, 12, but that is your signal, but you're going to dismiss it because you said your number is 15. Excuse me. So things to keep in mind here is that you can't ever measure your sample. You're always performing a test, and in that test is a component of background, and the difference is your sample. You can never measure the sample directly. So we might do, say, count the background for an hour, get 50, count our sample, get 150, and then infer that the sample is 100 counts. The problem is that the uncertainties don't subtract like that. So every time you test something, there's a certain amount of uncertainty, in this case, sigma squared, and they add to the sample uncertainty. Even though you're subtracting one value from the other, the errors are always cumulative. And there is some fantastic reading. I've got some links there. The Curry paper from 1966 was pivotal in all this, and everything I've read always goes back to that. There's a really good section in the Radiation Detection and Measurement 4th edition by Noel that talks about this, but with a more equipment detection sort of bent to it. It's also a little bit lighter on the maths. If you've got the time and if you remember your high school math, university maths, they're really good reads. If you don't like maths, I do not recommend them. So the first thing we define is this critical limit. So at this point, we've assumed that we've taken off the background because here background is, is 0. So let's say background was 100 counts over an hour. So you would take 100 off everything, but you still got that uncertainty of the square root of 100. So in this case, 10. And you want to make the decision, at what point do I draw a line and say, this is not a background count anymore? And that's your alpha. So we end up with a handful of equations for defining our limit of detection. Now, these are all assuming, this is all including background. I'm sorry. And they are all for counts only. This isn't counts per second. This is just, I've set my detector up, I put the filter under the detector, and I've let it go. It's taken 100 minutes or whatever it's taken, and I get a number. This is telling me what number I can say, yep, I have now definitively seen something. So when you send samples off to a gamma spec assay lab, when it's less than 0.5 becquerels per cubic meter, this is where those numbers come from. Again, unless you're running your own filter counting or assay lab, probably not going to use it. But sometimes if you get challenged, one of the things we've seen is that if the minimum detection limit is too high, the regulator here requires that you report your value as the minimum detection limit. So if you're using the OSL badges, I think our pandas have got an NDL of 0.1 per quarter, which means every year our workers were getting 0.4 millisieverts per year, just because that was the MDL of the badge. We changed providers, they had 0.01, and all of a sudden our 0.4 millisieverts became 0.04 millisieverts per year. We didn't change anything on site. It's just the NDL affected the dose assessment that much. And we have a lot of workers who, while they're working around norm, they're not radiation workers. They're very rarely getting any sort of serious exposure. But if your monitoring equipment and your counting equipment has high NDLs, that all translates to an elevated dose assessment for the year. But once you've got your counts, you can use the detector efficiency to get that in becquerels, or decays per second. Keeping in mind that the count is what the detector sees, the becquerels is what the source is doing. They are not the same thing. You have to use your efficiency, which can be a function of the detector, the geometry, attenuation, to get back to that activity, and then divide it by whatever physical unit you want, meters cubed, liters, centimeters squared. We will talk about that one. I mentioned to me, I'm not sure anyone heard it, that we do have DEMIRS norm guidelines floating around WA. It looks like this, which is somewhat intimidating, but I'll try and break it down as much as I can. So the background counts over the background time gives me my background count rate in seconds, multiplied by the sample time gives me the contribution from the background in my sample for the sample time. And this is the same thing here. So this is, we'll call it background and sample. This is also background and sample, square root, and the 4.65 we saw in the previous slide. So before, when I showed you the Curry equations, that was background removed. What's in the norm guidelines is including background. So it doesn't hurt to know a little bit more about the formulas you're using, because sometimes they will dictate what you have to do in your procedure. Do you add or do you leave? Sorry, do you remove the background or do you leave it in? And again, just following this blindly has led to mistakes. So I said I would talk about surface contaminated objects. Done a lot of work where we've got something with a little bit of norm in it, and we want to know if we can let it go or not, if it meets the transport definition of 0.4 becquerels per square centimetre, and there's some more stuff on that. We have to call it contaminated, and we've got to pressure clean it and do all sorts of stuff. So we can use our formula. We know what the diameter of the detector is. This is one of the, what's that, 7311 out of a Ludlam pancake detector. Sorry. We know what the area of this is. If I've got a background of about 0.7, that translates to 42 counts per minute. I can plug that through the formulas that we've done so far, including my background. So it's background plus this, because that's the formula we saw in the previous slide. And that, with the efficiency, gives me 3.1 becquerels. So if I'm getting, what have I got here, 75 counts in that minute, it equates to 3.1 becquerels. And if I divide it by the area of the detector, my minimum detection limit for this is 0.18 becquerels per square centimetre, which is fine. I can use that to definitively release something as not contaminated. But keeping in mind, I had to stand there for a minute to do that. And that's ignoring any other impacts from stuff around it. So let's do the same thing again, but only with 10 seconds instead of the 60. So my background's only 7 counts, which is not more than 10. My minimum detection limit is 15 counts, so background again. Here we go. Sorry, which gets me to 6.25, which is a significantly higher minimum detection limit, divided by the area, and it was 0.36. Now, keeping in mind that the limit of the definition, is 0.4. So standing there for 10 seconds, I am just barely able to make a claim that something is or is not contaminated. And keeping in mind that the total counts are below 10, so a lot of our assumptions about how this works kind of go away. It does. I mean, your background was 7 and your limit of detection was 15. It does kind of support that idea that double background works, but you need to get there through this math. You can't just say, oh, we use double background because that seems reasonable. You need to be able to quantify that at some point. Big assumptions about other nearby sources. I've never ever had to inspect something where there wasn't something hot next to it as well. You've got other hazards associated with these test times. So if you've got someone standing there for 10 seconds to a minute, I mean, it might be inside a confined space. You might not want them just standing there on a slippery surface, suspended by rope access, or just generally in a confined space for any longer than they need to be. And the last one is, of course, the radiotoxic alphas, which has got an even smaller limit. Generally, we don't see that in mining, right up until you talk about scrubbers, dealing with the off gas where they've got polonium. And that polonium-210 is considered radiotoxic, so it has a release limit of 0.04, which I am personally struggling to get something to be able to measure down to that in the field. Alpha current dust filters. So this is generally what's used in WA. I'm not sure what's happening in the other states, but we'll use occupational hygiene methods to collect dust on a sample filter. Our backgrounds will go for 15 hours, and we'll get anywhere from 40 to 100 counts. For this presentation, we'll call it 70. Our sample times are about 2 hours, and gives us an MDA of approximately 10 millibecquerels, 10 millibecquerels per cubic meter, which is a very, very small amount of dust. But that dust, over a long enough time period, like 2,000 hours at a nominal breathing rate, can start to add 0.2, 0.3 millisieverts to somebody's dose. So that MDA at 10 millibecquerels per cubic meter is still going to contribute a lot to a member of the public, a non-radiation worker. So we need to be mindful of that when we report it to the regulator. So doing these sorts of calculations, doing a background and knowing what you're saying and tuning your sample time and background time to get that number lower is something that was baked into some of the guidelines that we've got. There is some variation happening at the moment, but generally it's always a really long background time that goes for nearly a day, and then an hour to 100 minutes for the sample. So subsea norm inspection. I haven't mentioned it yet, but everything we've been talking about is a passive inspection technique. That is, you stand there and you wait for the radiation to come to you. You can't really do anything to speed it up. You can't do anything to improve the resolution other than just wait longer. When I was working in that industry, they didn't like that answer at all. They used active inspection techniques like ultrasonics and radiography and stuff like that. And they just didn't like the idea that we had to hold the meter somewhere for a really long time. But in this scenario, you would have your detector, usually in some sort of vessel or enclosure so it can go in the water, held onto by an ROV with its manipulator. The ROV would fly over to whatever you want to inspect, and then the operator, who's up on the boat somewhere, would then have to keep it stationary there for however long you say. It came with some pretty big challenges. So the geometry effects inside the pipe. What you can see on the left, that is a production pipe, not a service flow line, but that is a lot of scale. The dose rates we were seeing around that were 30, 40 microsieverts an hour. But if you don't have it neatly distributed the way it is here, let's say it's all at the bottom, does that give you the same response as though it is all on the top? And if there's a lot of it at the bottom, but the flow line's full of water, is that going to attenuate it out and you won't be able to see it? So when you've got a lot of norm and you can easily detect it outside the pipe, you are far beyond any sort of threshold where you can say, oh, I'm just going to recycle this. You're chasing really, really low numbers like we saw before at 0.4 becquerels per square centimeter, but through water, through pipes, through more water, through the housing of the detector, and the motion of the ROV. So if there's a cross current, your ROV is going to slosh back and forward, and that's going to, it's going to reduce your detection sensitivity, probably increase your detection time, and most importantly, it runs the risk of smashing your detector into whatever it is that you're trying to measure. So the ROV operators will try and back off a little bit so they don't bang it into the pipe, but then it doesn't take a lot of water for your signal to be almost completely attenuated. So there's a real dance between getting it done well, not breaking stuff, and just dealing with the environment. But there are some things working for you. So the low background from the sands, seabed generally has a pretty low background. And whatever background there is, particularly the low energy gammas, will be attenuated out by the water. Generally, what you can see there is radium 226, 228, really high energy or relatively high energy gamma from one of those decay products. So you're trying to measure a high energy gamma in a field where all the low energy stuff has pretty much been stripped out. So there are a few things working for you, but again, it's a very difficult application of just stand there and wait. So there are some other options, which is moving the detector inside the pipe, which is a great idea right up until you meet a blockage, in which case your detector is now and the whatever you're using to propel it is now stuck. You can use the biggest insulation crystal that'll survive. So a lot of these low count rates I've been talking about are generally from GM tubes, Geiger-Müller tubes, where the count rate is, say, 17 counts per second per microsievert per hour. You go in there with a scintillator, that 17 becomes hundreds, if not thousands, and a lot of your counting problems disappear. The problem is the size of the detector. The crystal itself is only about 2 inches, but the photomultiplier tube on the back, it's made out of glass. It's not going to enjoy getting bashed around, and they're relatively hard to source at the moment. Again, there's some really good stuff coming down the line with silicon photomultiplier chips. So all that glass is replaced with a silicon wafer. The crystals are still the same, much smaller package. I'm excited to see how that stuff works out. Crawlers, so instead of a flying ROV, put something really heavy on tracks and just drive it around the seabed, looking at stuff with still got this manipulator, but if you take your hand off the controls, it just stays where it is. That's probably I think that's a really good opportunity to explore for somebody. And the questions you ask before you go into this oil and gas inspection is, what's the purpose of it? So is this an occupational health and safety thing? Are we worried about workers when they come up to the surface? In which case, a dose rate of 0.3 microsieverts per hour, which is relatively easy to detect, is fine. You don't need to get right down into the becquerels per gram on that one. Are you decommissioning? You just want to leave the stuff in situ, in which case what you're doing is feeding into an environmental impact assessment. And again, you need to know what the tolerance levels are for that. That's also an open question. There was some great research out of the National Decommissioning Research Institute a couple of years ago on that. Or do you want to export it for disposal somewhere else? In which case you need to be able to fill out all the Class 7 declaration paperwork. And that should hopefully drive what is your limit of detection. There's no point getting down to ridiculously low numbers if that's not what you need. Do you need, you might just want to do a quick pass, make sure it's safe for workers, bring it to the top, and once it's on the vessel or even back on the beach, then you do your highly invasive radio assay. And the other question is, does this need to be done passively via gamma emission? Is there another way to detect the norm inside the pipe? There's some really early stuff going on with that, like neutron bombardment. I think that was with mercury though. But is there another way to do this? Radiation is really easy to detect, very, very difficult to quantify. So in conclusion, when performing passive detection for low signal to background sources, time becomes a very significant variable. That's probably the biggest lever you've got when you're doing this. Your next question would be, should I spend more on sensitive equipment or labor? Maybe you can afford to just have a technician stand out there for a week, in which case, give them the procedure, go for it. If that's a really dangerous proposition, then you might need to go spend some more money on your equipment. Definitely start by determining the sensitivity needed to achieve the outcome. There's no point overcooking it. Likewise, you don't want to go out there underprepared. Rules of thumb are great. I use them, but that double background thing is a really good screening level when you go out there. But you need to be able to quantitatively demonstrate why you're doing that. Not just go, Bob told me. It needs to have something behind it. And I think what surprised me most of all when I started looking into this is that none of this is new. This is all really old stuff. It was a very active field back in the 50s and 60s. They literally wrote the book. People still refer back to that Curry paper from 1966. It just seems to be hidden. So looking through it, I mean, when you publish something or you write a textbook, the maths is always rigorous. And rigorous maths is really impenetrable. There's lots of squiggles, there's lots of leaps of faith. And if it's been a while since you've done calculus or probabilities and statistics, it can be really difficult to get through. It took me a very long time. I had to go back and reread a lot of stuff. It is all out there, though. It's like I said, there just doesn't seem to be a bridge between, highly rigorous maths and Wikipedia article. There just doesn't seem to be something in the middle to help people get a little further. So thank you for listening. That was my presentation, including the break in the middle, the intermission. I guess we'll throw open for questions now.
Thank you, Dean. I really enjoyed that. That was, as you summed up, an excellent way of putting the maths at just the right pitch. Not more detail than we need, but not oversimplified as to forget the real point of it. So thank you. Any questions, anyone? If you've got them, please pop them in the chat. Otherwise, you should be able to pop up your hand somehow to signify that you want to ask a question. And while we wait to see if any of them come through, I've got a question. So you've explained very well the challenges of where you have an instrument, and especially if it's, say, looking in counts per second, and you can use some of the measurement statistics to identify if something is above your background and look at detection limits. One of the other challenges I'm interested in that you would have no doubt come across is when someone's done that and then they come back 6 months later to repeat it, but they've got a different instrument and they're trying to compare, the results now with a different instrument that will have a different CPS, for the same exposure sort of situation. I just wondered about how you approach that in your industry.
Yeah, look, we've had the same problem. We've got mines that were started back in the 80s using, really, really old equipment that's long since been decommissioned. What I'm trying to get people to do is to go measure something that probably won't change. So for our Cataby operation, I said, look, let's go survey the post office. That's probably going to be there a while. And if you've got a point of reference that hasn't changed, you can go back with meters and verify that the response, you've got 17 counts per second, but now it was this new unit, it's 25 or something. That's the only one I can do. It's not a calibration. When dealing with norm, I'm very suspect of calibration because it's only calibrated to that 662 keV cesium 137 peak. And when you move away from that, your energy response with the detector can be wildly different. Certainly with those scintillators, with their really, really good counting, they overread at nearly 10 times for some of them at the low energies. And the low energies is what you're primarily going to go see out in the field. I would recommend that there is some agreed location or standard that people can go test their measurements against, just so we are all talking about the same stuff, if that makes sense.
Yes.
I believe that Queensland Health has got some concrete, you got some concrete pads set up for something like that.
We do some concrete calibration pads with known ingredients of norm, more thorium rich than uranium rich, but a bit of both. So that we can look at dose rates up to about 300 nanograys an hour.
And that would be great. I mean, again, cesium calibrations are awesome, except they're really high flux and they're only one energy. The idea of having that touchstone that you can go back to with a new meter and go, well, how does this work here? You will see variations based on the energy response. The regulator here is also very keen to make sure people know their energy responses too, for that reason.
We have a question in the chat from Safe Radiation. Saying thank you, Dean, for a lovely presentation. What is your suggestion about spatial variations in the measurements? That is, several measurements over an area will have variations both naturally and due to contamination.
Great question. You need to have some idea what those variations are. There's a few ways you can do this. One, sampling confidence. So how many samples out of 100 do I need to be 90% sure I got at least one of the top 10%? There's a really good NIOSH 1977 document on that. I think it's Technical Appendix A, which is if you've got a population of something, in this case it's people, how many samples do I need to take of people's inhaled air to know that I'm confident of getting that, one in the top 10%. But that applies to space as well. Like if I've got 100 hectares, how many samples or how many hectares do I need to do to be sure that I'm X% confident I've got at least one in the top 10% or whatever it is. So again, you need to frame that question, and then the next question would be how confident do I need to be? What am I using this for? Is it is it land going back to agricultural use? Is it going back to native veg? Is it going to become a kindergarten? I guess you would start at the end of that process and say, what am I trying to achieve here? And then work backwards and say, right, well, how confident do I need to be along the way? It's one of the irritating things about a lot of this is that it's about confidence in your results. I don't get to never speak in absolutes, never 100% sure.
I agree. There's another comment from Simon Sharp in the chat, just saying also that you could use the guidance from the NEPM, the National Environmental Protection Measure, for the sample size across a known volume or area. That's another approach.
I haven't seen that one, but I suspect they're almost identical. There's something called, I think it's the hypergeometric function, which drives a lot of that sampling stuff, which is like, what's my population size? How big is the group inside that population I want to get at least one from? How big is my sample size? And how many successes do I want to get? That is even a function in Excel, which I use extensively for my occupational hygiene sampling plans.
Have you adopted visual sample plan at all?
No.
It's a software application which is relevant to this sort of discussion. Some people have used it. We did have a webinar a little while back related to it as well. But it's a matter of sort of being able to plug in what you want to see across what sort of area, what sort of level of detail you want to achieve, and then it helps you to structure your sampling to meet that, to achieve that.
Okay. No, I haven't seen it, but that sounds like it would answer a lot of questions in our health and hygiene management plans over here, and also the radiation management sampling plans.
Yep.
And I guess that's a balance that we certainly have over here, which is you want to do as many samples as possible to be sure, but you've also got a budget telling you to do as few as you think you can reasonably maintain to get that level of confidence. And there's also putting dust pumps on people. Again, it doesn't make you super popular on site.
Yep. Simon just asked what the program I mentioned is, visual sample plan. I'll pop it in the chat so that people can also explore themselves. Any other questions from our participants, our audience? Probably a lot to digest with the maths in there for Friday afternoon.
If someone's interested in the maths, this will keep you amused for years. There's so much in there. But at some point, I had to go back and do paid work. So,
fair enough. Fair enough. No, but I think it's an excellent way to cover off being able to have confidence in the numbers at those low levels, and something I'm not sure you really gave a lot of explanation to, but if people aren't aware, sometimes the difference between saying yes, this is a problem, or no, it's not, is got big dollars and big time associated with it for businesses. So therefore, you want that confidence. You want to be able to say, "Yep, I have a lot of faith in these numbers," and I can say with hand on heart that this exceeds a limit or that does not exceed a limit, because the implications for the people downstream can be quite substantial.
Yeah, I mean, a lot of us are statutory appointed RSOs, which means in the future, if there is a problem, it does come back to you. You're not an employee, you've been appointed this position by the regulator, and your advice to the operation is serious.
Indeed. All right. Riaz has just added something to the chat as well, just saying, suggest considering your work be published in a journal such as the Journal of Radiation Protection and Research. So that's something to keep in mind. That's jrpr.org. And I believe that's an open access one. And I also believe it's free to publish in. Riaz will correct me if I'm wrong, but two good incentives there to publish.
Yeah, Riaz, if you want to reach out, very keen to get this spread further. Again, the mentoring I did, there just wasn't access to this stuff. It was all really high level or really low level.
Well, thank you once again for everyone participating, but especially to Dean for, that really interesting presentation. I look forward to being able to refer back to some of those numbers in your slides and the maths when it's available online for us to view again. I'll also take this chance just to remind everyone that the ARPS conference is on again this year, of course. So it is in October, the 20th to the 24th in 2024. So that should be easy to remember. We're at Coffs Harbour. And the other thing I'll let people know about is the ARPA, so the International Radiation Protection Association conference number 16 is on in Orlando from 7th to 12th of July. So that's coming up super soon. ARPS is going to have an attendance there, and especially so because we are bidding to win to host ARPA 18, so 2032 in Darwin. So anyone who's from the ARPS community that's going to be present that hasn't already sort of made themselves known to the ARPS executive, please do so, because we'd love to have you involved in supporting us over there with that bid. So thank you once again, everyone, for your time today. Really appreciate it. Thank you.